Hello, everyone. Welcome to today's globally broadcast series. In today's presentation, we are going to share with you the modular spectrometer's knowledge and application. Whether you are a freshman or the senior engineers, we are going to share some basic knowledges and deep knowledges with you. So you can learn some knowledge from us. You can make yourself to know the know-hows of the modular spectrometers. Okay, thank you. Let's start it. So in today's presentation, we are going to introduce from the following 5 parts. Part 1 is the working principle of the modular spectrometers. And part 2, we are going to introduce the internal structure and the configurations of the modular spectrometers. And in part 3, we have introduced the main performance parameters of the spectrometer. And part 4, we will introduce the common models of modular spectrometers from the opto-sky. And finally, we can give you some examples about applications. In these pictures, you can have a general ideas of what the modular spectrometers looks like. Do you see that they all look like modulars? Yeah, that's right. Especially you can see this is ATP 2000. This is the most popular models sold vast quantities for the OEM projects. And because they are have a high performances to price ratios. And also we have the most miniature Raman the modular spectrometers. This one, you can see the size is only a bit larger than a coin. And also we have the longer spectrometer. You see it's longer. So why? Because it's being installed the fan inside. And it has reserved the ventilation port for the heat ventilation. Because they are the cooled spectrometer, right? And this is the mid-IR spectrometers. So in order to introduce so you may ask, what the modular spectrometers used for? We use this vivid cartoon flash to introduce it. And you can see this is the incandescent light. You can see the light generates the white light. But when it shoots into the spectrometer and being analyzed, we can see that it has the rainbow colors. And then a spectrometer will export this data to the PC. We can export this the left spectrum. The spectrum can tell us the wavelength information, and also this is the intensity information. So the next question is, what's the principles of a modular spectrometer? Usually we have a light access to shoot on here, and in this place we have a slit size, and the slit size can form a parallel light shoot on the in this place. This is the grating. Grating will have a dispersed light. Will disperse the light to here, and this is the focus mirror. Will focus the disperse the light to the dictator. The dictator can transform the optical signals to the electrical signals to this way. So this is the general principle of how the modular spectrometers work. And usually we call the modular spectrometers fiber optical spectrometers. So why? Because usually we use optic fibers as a signal couplers So it can dictate light coupled into the spectrometer to make the spectrum analysis. So we call it fiber optical spectrometer. And also they are named microspectrometer first because it has the compact size. And then what's the main components of the spectrometer? So we have the entrance slit in these places, and secondary we have the collimating mirror, and thirdly we have the grating in this position, and also we have the dictator in these positions. So in here you can know what are spectrometers used for and its principles. So next, we are going to introduce in details what are core components of the microspectrometer. Firstly, we have mentioned slit. In this position is the slit. Slit is just look like this one. This is the slit. And usually the slit, what's slit? Slit is used to form a point source. So you can ask what if the slit is narrow, the resolution is better, but the intensity is weaker. And next, we have the grating in these places. Grating is a very important component. It can decide the wavelength range and the resolution. And next, you can see here is the dictator. Dictator can transform the optical signals to electrical signals, and it can form a spot beam, the stripe, just look like this. And we can put this spot beam stripe in the back of the linear array. In this linear array, then we can have the export the spectrum. We can export the electrical signals. Next, we are going to introduce the functions. So we know that modular spectrometers used for measure the light intensity in the range of the UV, visible, and NIR and IR. So because it has the advantage of the size is very compact and accuracy is very high, and they are flexible in use, and the reliability is sound. We also have mentioned working principles in previous PPT and the main components. So we will mention here a bit about application. So applications, modular spectrometers usually used to measure colors, absorbance, and concentrations, and like emission spectrum, LED, thin film, thick, and also used to monitor the process coating in vacuum chamber and oxygen concentration sensors. Some customers also use to identify gemstone components, and usually they measure the fluorescence and more. And in the later PPT, we are going to show some examples with you about this application. First of all, let's introduce the component structures of the fiber optic spectrometer, and I will use this have some here. The first one is the SMA head. In this places is the SMA head. The second one is the entrance slit. In this one, just behind the entrance slit, there's a long pass filter. There's a long pass filter. And the fourth is the collimator mirror. It's the fourth. And the fifth in this place is the grating. And in the sixth, we know this is the focus mirror. And seventh, we also usually use the current mirror. And if you have the 8, the second order sorting filters, and also 9 in these places, you can 8. You can have the dictator. So 7, 8, and 9 all installed in this position. And if you have if this spectrometer is cooled, you can also have a T coolant or temperature sensors in these places. And the 11 cannot show in this picture because it's in the back of this spectrometer. It's a signal processor circuit. We have to emphasize here is spectrometer is a customized product. So what can say is a customized? Because it can be it can produce according to customers' demands. You can have the wavelengths, you can have the resolution requirements, and you can have a signal to noise ratios. So before production, product managers should communicate well with the customer to know the customer's application and his requirement. Then the product manager will configure the most optimal components in order to meet the performance demand. However, as soon as the product manager has configured the most optimal configurations, we begin to productions. After production, every performances are fixed and cannot change anymore. Even if a customer raise that we need to use for another applications, but sorry, it's not allowable to change the performance after the production. So before production, we need to well communicate all the parameters and configure the best optimal components for your performances. So next, we are going to introduce how product managers can configure a spectrometers for your application. They usually need to consider firstly is the wavelength range. By selecting different gratings can customize any wavelength range. So the more the grating lies, the narrower the wavelength range, but the resolution is higher. And also, we also want to realize the both wider wavelengths and higher resolution. How can we do that? We can use multi-channel spectrometers to combine together. Later, when we introduce the wavelength range page, we will introduce more in details. And secondary is the sensitivity. In general, sensitivity decided by the grating efficiencies and incident fiber or slit size. And also we have the optical mirror performances, and we have the current mirror available or not, and also detectors sensitivity. And then third one is the optical resolution. How to improve optical resolution? We can use the higher grating lines, and we can use the narrow slit size. And thirdly, we can select different dictators, such as if you want to the UV enhanced, we can select a UV enhanced sensor. If you want the best performance in visible, we can use silicon CCD CMOS or PDA eccentrics. And if you want the infrared, you can use the Inga S CCD paraelectric eccentrics. And fifthly is we have the multi-order diffraction effect. How to eliminate multi-order diffraction effect? Product manager can consider to install a long-pass filters at a SMA entrance port. And they also can add the second-ordered sorting filter like a linear variable filter or partition coating to realize it. The last one is the straight line. Straight line is the harmful light need to consider to eliminate it. So having introduced the how the product managers can consider all these 6 factors. Next, we are going to introduce the core components and functions of a fiber optic spectrometer. So when we mention about a fiber optical spectrometer, the first is the topological optical structure. Topological structure is in generally decided by the spectrometer's resolution, sensitivity, straight line, and size. Such as we have 4 types of the topological structure of the optical bench. First one is the cross-CT optical path, M-shaped CT optical path, and concave grating optical path. And fourthly is transmission grating optical path. And the second is we need to consider the dictator. Dictator is the most important component to affect the spectrometer's performances. It's because the dictator can decide on the sensitivity. It can decide the signal to noise ratio. It decide the dynamic range, and decide the maximum wavelength range. You know, dictator is the main part of the cost. So the cost of the dictator can decide the spectrometer's dictator. If you use the core dictator, the cost is ranging from decades of thousands. And if it's an uncooled dictator, they may just cost few hundreds. So this make up the main cost of a spectrometer. Thirdly, now to mention grating, we have introduced before. The grating can decide the spectrometer's wave ranges, and it can greatly affect spectrometer's resolution. And fourthly, the incidence lead size. Incidence lead size was affected the resolution and the sensitivity. We have mentioned before the smaller the lead size, the resolution is better, but the sensitivity is weaker. And also, the lead size can also affect straight lines performances. And the fifth one is the current mirror. Current mirror can improve sensitivity about 3 times. So although it can reduce a bit of resolution, in this sketch we can see what the current mirror's working principle. This is the dictator's head. It's just about 200 micrometers. And if the spot beam is generated like in crescent moon, but is thin and long, you can see the most energies cannot be absorbed by the dictator. So if we add the current mirror, we can compress this crescent moon to the fatter and shorter. In this one, we can absorb the most 80 to 90% of light energies to the dictator. So it can improve their sensitivities about 3 times. And the last one is the high order diffraction filters. Grating features decide the generation of higher order diffraction. Filters is used to sort out the higher order diffractions in order to prevent disturbance. We also will have a detailed introduction about this in the latest PPT. First, we have to introduce to you about topological structure, because it's the most important, the most core component of the spectrometer. First one is the cross-CT optical path. We know cross-CT optical path used most in the spectrometer, for it has the compact size and the sensitivity is very good. But not to forget about M-shaped CCT. M-shaped CCT, you see, it's just like a capital letter M, and it's an unfolded optical path. So we call it M-shaped CCD. M-shaped CCD has a bit larger size, but the resolution is better, and straight line is better, and the reliability is very good. And also we have a concave grating optical path, and this is the light we shoot in here, and this is grating can disperse and also focus the light and to here. This is a very simple optical path. And also we have transmission grating optical path, and we have light shoot on here, and in these places we have the grating can disperse the parallel lights. It make a turn to shoot on the focus mirror, and focus mirror can disperse lights shoot on the detector to transform the optical signal to electrical signal. So in this sheet we compared the M-shaped CT and cross-shaped CT because it's the most common optical topological structure. Both have their advantages and disadvantages. Like cross CT, the size is more compact and sensitivity is better. But M-shaped CT, you have a higher resolution but a lower straight line. So for the high-end Raman spectrometer, we use quite a lot of M-shaped CT spectrometers. In optoskies models, we have M-shapes. We use the third letter 3 to indicate M-shape CT. So if you see our model number have 3, in the third number is 3, you can know it's the M-shaped CT. We also divide to the uncooled spectrometer. We have 3 series uncooled, and we have a cool one. We have 5 series. But for cross CT, we have the most popular ATP 2000 and P, ATP 2000 series, and 3000 series. And we also have a cooled one. The most scientific class is ATP 6500. And next, we are going to introduce the CCD dictator. We have mentioned that CCD dictators decide the most cost of a spectrometer. So also it's the very important component of spectrometer. You may ask, what's the principle of it? Here, we are going to give you a vivid introduction of the dictator. Firstly, when a photon shoots on the light, it will generate the ionized and it can accumulate it here and wait for readout. And in these pictures, we can make a vivid examples to tell the principles of the dictator. When a photon shoots on the light, it's just like a rain is coming down. And this is the bins. We call this a small bucket. We can store rainwaters here, just like stored electric charge. And different bins can store different volumes of the rainwaters. After store the rainwater in the bins, we will pour down the rainwater to this siphon pump. This is the ship register, and gradually pour down here, and finally we can have these larger cylinders to have all the rainwater volume stored here. And store here, we have all the electric charges can be read out and transformed to the voltage. So the process of this pouring rainwater down pour rainwater down is the working principle of the dictator. So we mentioned that raindrop indicates the photons. Raindropping is like a photon shoots on the light. And when we use the correct rainwater indicator, the CCD, to detect the electric charge. So this is a piezo. A piezo can store the electric charge. So this the bucket, small bucket indicates the piezo. This bin is the piezo, and bucket volume indicates the how much each piezo can hold. So how much rainwaters can be stored. And also we have siphon pump indicate CCD shift registers. We need to pour down to the register shifts and gradually from here to here. And finally, rainwater cylinders indicate CCD output amplified. So we can use the rain is coming down and use the rainwaters pouring out processes to note how the CCD dictators working. It just need to transfer the electric charge to the voltage, and in these large cylinders, you can read out the voltage. So after introducing the dictator, we also would like to introduce the dictators. What the core parameters of the dictator? Mentioning about the dictator is needed to know what's the maximum working range of the dictator. By selecting because the working range of the dictator can decide the spectrometer's dictator. And secondary, you can see in this picture, this is Hamamatsu model's dictator. These dictators can cover the wave range from 200 to 150. And secondary is the sensitivity. Because dictator sensitivity is the most important parameters of the spectrometer. Take an example also of the Hamamatsu model's dictator. We have the S10420, and this one in the UV range starts from 220. The quantum efficiency is very low. But the S11510, the 200 this wedge, the photon efficiency is 70. It's over 3 times higher than these models. So if you want to use the UV range, you want to improve the UV range sensitivity, surely S10420 have a better response, sensitivity response. However, if you want to focus on the NIR range, we have the NIR range usually covers from 900 to 1100. This S11510 models have a higher photon efficiency. So we choose these models can have a higher sensitivity than this one. And thirdly is the dynamic range. Dictator's dynamic range decide direct spectrometer's dynamic range, and most spectrometer's dynamic range use the dictator's dynamic range directly. And we can know that dynamic range is used the saturation intensity peak to divide to the noise. This is a formula. And we have also mentioned the force signal to noise ratio. Dictator signal to noise ratio also decide the spectrometer's signal to noise ratio. We can have an average multi-measured peak to measure mean square error. And these two we will introduce in details in later about how to calculate it. And then we turn to the cooled or not. Dictator cooled or not, we say is also the very important parameters. Because if it's a cooled dictator, it can effectively reduce the dark current and the readout noise. Because it reduces the noise. So both dynamic range and signal to noise can be improved. So you can see these two important factors improve, so the performances can be improved quite a lot. When we ask the cooled dictator or not, you can ask if the one-stage cooled, two-stage cooled, three-stage cooled, or four-stage cooled. And then we introduce the 5 key parameters of the dictator. Then we move to introduce the dictators, the models. Here we use the blue colors to indicate the visible UV and visible range dictator. We have a silicon CCD or CMOS. It's very simple. This one. And also, we have a silicon PD array. We have BT CCD and BT FFT CCD. From the left to the right, the performances is higher and higher. Such as we can see the silicon can cover the range from 180 to 1100. It has more pieces and readout circuit is very simple. But for PD, we also have the 180 to 1100 nanometer, but signal to noise ratio a bit higher, and it has less pieces. And in BT, it has the higher signal to noise ratio, and it has smaller dark current. It has longer integration time, but BTTT FFT has the best signal to noise ratio. It has the longest integration time and the ultra low dark current. So from left to the right, the performance is gradually rising. And below, we use the red color to indicate this is the in NIR is the infrared range. Firstly is the INGA ACE. INGA ACE response range covers from 0.9 to 2.5 micrometers. And we have a paraelectric. It can cover from 0.1 to 100 micrometer. And I would like to give you examples of an automatic door use a paraelectric dictator. And when we go to the washroom, we use auto wash hands dictator. Sensors also use this paraelectric sensor. And also we have a mercury cadmium telluride. It's the MCT. It has the higher sensitivity and it requires the lower temperature, and it can faster scan. And not to mention the indium arsenide. It have a wavelength cover from 1 to 3.8 micrometers. In these pictures, you can vividly see different NIR materials response range. You can see J22 INGA ACE. It starts from 1 to the 2. And we also have a J23 INGA ACE. It starts from here to 2.5 micrometers. And you have a J12 indium arsenide. It can respond from to the 4 micrometers. And this is the media cadmium telluride, and this can to over 10 to 11 from here to here. And we also have over to the 20, over 20. So many FTIR use the MCT dictator. So After introducing the dictator, it's needed to compare the CCD and the CMOS, because some people usually ask what's the difference about the CCD and CMOS. Actually, CCD and CMOS in the front sections are the same, like photon electric conversion and the charge correction. Both CCD and CMOS is the same. But the difference is the CCD can charge transfer, and it can charge voltage transfer to this. So CCD is a transfer simulated signal, but CMOS it can transfer the piezo. It's a digital. It can internally. It can transfer to the voltage. It's a digital signal. So we can see from here, CCD is export the charge, CMOS export the voltage, and the CCD is output a simulated signal, and the CMOS export the digital signal, and obviously CCD have a better performances, like its noise is lower, and the fill factor is higher, and dark current is lower, and uniformity is higher, and dynamic range is higher. So all these 5 factors have know that the CCD is better than CMOS. However, CCD have a more complex system, and the power consumption is bigger, and it has a larger breadth for vertical breadth is larger. So this is the weakness of the CCD. However, CMOS have advantages than the CCD in these later 3 parameters. In these pictures, we can more vividly know what's the CCD and CMOS relationship. You can see in the front section, CCD and CMOS are the same, but CMOS has more A&D transferred, because CMOS is based on CCD, and it increase the signal readout circuit, so it can make the signal process circuit to digitalize the circuit, so it can finally export the digital signal. So next we are going to introduce the grating. So grating, we say that the grating is used to disperse the light. So grating indicates the light dispersion capability. When the white light shoots on the grating, it can disperse to the different wavelengths. Because the grating is the important component used to the split light. So select a good grating can decide the system's performances. Grating consists of a large quantity. Grating, you can see this large quantity of parallel slit light in lines, and they are the center-wise and the same interval. So different wavelengths have a different diffraction line emissions and a certain angle. And we have a plane grating. For we say the CT and M-shaped CT, they are plane grating. And we say the concave grating, it looks like this. And we have a transmissions grating. It can transmit through the grating to different lights. So we can ask what the grating density. So grating densities, we can ask how much grating densities per inch. Maybe we have a 500, we have a 1200. lights. So the higher the lights, the better, the wider the light spread. So the resolution is better. And if we fix the grating densities, we can have a breadth wavelengths. Breadth wavelengths can decide the maximum diffraction efficiency of the grating. So we can, by selecting the breadth wavelengths, we can set the certain range of the wavelengths, the better response efficiency. And thirdly is the breadth efficiency. Breadth grating efficiency is used the ratio of single light to divide to the certain orders, so and entrance light, so that breadth efficiency can also affect the sensitivity. Next, we move on to the incident light. This is the incident light. And also we can introduce the slit size and resolutions relationship. We have two types of slits. We have a fixed slit. We have a changeable slit. Because the slit size can directly decide the resolution. We have a usual slit width like a 5 micrometer, 10, 25, 50, 100, 20, 300, and 500 micrometers. We need to emphasize the advantage of the fixed slit. Fixed slit, it has not movable parts, so reliability is better. However, the disadvantage is the resolution is fixed before delivery. It cannot be changed according to customers' different application. So because the market requirements, customers sometimes need to change application. So we have the changeable slit. So the advantage is it can change the slit and change resolution according to customers' demand. However, the disadvantage is the slits changed by the customer. If they don't adjust well or it has a bad adjustment, it can affect the resolution and straight line, so to affect the performances. And so we usually use larger core diameter fibers to improve the resolution by wider slit, and we also introduce more light energies and improve the sensitivity. We can use the larger diameter fibers to achieve the better sensitivity. And also we use the fiber direct in, so no need so fiber direct in. So fiber diameter is the slit width. We have a 9, 50, 105, 200, 400, 600, and 1000 micrometers fiber diameter. The advantage is slit width is the fiber diameter. It can decide directly the resolution. However, all lights can be effectively used. However, the disadvantage is the smaller diameter like 9, the fiber coupling efficiency is relatively low. This picture also shows the relationship of slit width and sensitivity and resolution. It is very vivid. Different color indicate the different slit size. We have a 5, we have a 200. You see, in the blue one, the 5, the resolution is this one, so it's very short. So resolution is the highest. And if you use 200 and 200 micrometers, the resolution is so wrong. So for the narrow slit size, the poorer the resolution. However, the single node is the highest. Single node can do this, but this single node is only this. So it can vividly tell the relationships of the sensitivity and the resolution and the slit size. And so the slit size can affect the performances. So how can we use a way to solve the slit paradox relationship with resolution? So so the engineers think about this is the yellow striped part is the efficiency can be obtained. However, obtained from the slit. However, if we can use a light of the slit size, and we can have a light of the light in this, and also we take a pictures of how the light goes through the slit side is just only this short, and this is the fiber through the Raman signal, and this is a 15 micrometer slit. If we use a light of the slit, we can have the more energy coming, and we have a higher light intensity. And next, also need to mention the color mirror. The color mirror, this is the color mirror looks like. The color mirror. Before we have already introduced, this is the dictator haze. Dictator haze usually 200 micrometers, but the spot beam usually looks like crescent moon. Is long and thin. So only this can be absorbed by the dictator. Others energies is lost. So if we use the Lister's current mirrors, we can compress this long crescent moon to the bigger and shorter one. So 80 to 90% of the energy can be absorbed by the dictator. So current mirror is usually installed in these places. So current mirror can improve sensitivity about 3 times. Although it can reduce a bit of resolution. But if a dictator pixel height, suppose if we have a longer dictator height like this one, we have a so long. So what the problems it can bring us? Because if the dictator pixel height is so long, the cost should be rising sharply. And also it can have a bigger dark current and bigger noise. So if we use the current mirror, we don't need such a big pixel height can solve it. And this picture is in another angle to explain what the current mirror's working principle. Firstly, the light can shoot in this direction. It's shooting in here, but the pixel is such tiny. So most energies has been lost. It can only few can be absorbed by the pixel. And this one, if we use this current mirror, we can focus this light to the pixel. Most pixel can focus the light here. So current mirrors can improve the sensitivity about 3 times. After explaining the current mirror, we have to also introduce the higher orders diffraction and how to solve the higher orders diffraction. In this we can see, suppose this is the 200 nanometers. We have the first order peak. The first order peak is usually the useful peak. Is the useful. However, it's the second order peak, the third order peak, and fourth order peak. Suppose in the 400, and in the 600, and also in the 800. They are harmful peak. This harmful peak could affect the measurement result, so we don't need it. So the question is, how can we eliminate these harmful peaks and only need this useful peak? So we have a solution. We can use linear variable filters, LVF. This is the different color indicates the different wavelengths. The advantage to use LVF is it can export smoother the spectrum, and it's easy to produce. Disadvantage is it's very costly, and also it has very few categories to choose, and it cannot be changed. So the other solution is we can use the partition coating, because we know in the peak 400, this peak, the light is coming from the 200s, coming from this one. So if we can partition coating this area, so the light cannot cannot go through here. We block the light in 200 nanometers, so the peak of this will be eliminated. The advantage is the partition coating, the cost is much lower, and we can customize, so we can have more categories for selection. But the disadvantage is in the front section, we need the UV light. However, in the later section, we need to block the UV light. So in the middle, we have a transit band. This transit band can cause the spectrum sunken. So spectrum cannot look so nice. And also, partition coating is difficult to design. So it requires a good design to attain the best process. So we can adjust the opticals, and it's easy to introduce. So this is the higher orders diffraction, and we can solve this. So in the part 1, we have introduced the working principles and whether factors can affect the spectrometer's performances. In the part 2, we are going to introduce the internal structure and configurations of the spectrometers, so that you can know more about the spectrometers. Firstly, we need to introduce you about the core performance parameters. We introduce 8 important parameters can decide the spectrometer's performances. First one is the wavelength range and resolution. We have 3 types of resolutions definition. Firstly is optical resolution. Second is the pixel resolution. The third one is wavelength resolution. And secondary is the sensitivity. In the condition of inputting the same light intensity, signal intensities relates to the slit size can decide the sensitivities, and optical mirror efficiency decide the sensitivity. Grating efficiencies decide the sensitivity, and dictators sensitivity decide So spectrometer sensitivity is the very important factor. And also we have the signal to noise ratio. Signal to noise ratio is especially important in quantitative analysis and online analysis. It can measure the accuracy, and we can know the minimal detect limits. And signal to noise ratio is mainly decided by the detected signal to noise ratio, and it has less effect on the optical platform. And also we have the fourth is the dynamic range. Dynamic range is use the maximum intensity output to divide the noise, and is the one-time spectrum's performances. It can export one spectrum and another spectrum's performances, and it also can make the spectrum looks more elegant. And fifthly, if the spectrometer is cooled or not. We mentioned before, cooled can bring advantages of lower dark current, lower noise, and higher stability. So we also have the straight line. So next is the straight line. Straight line is a harmful light. We don't need it. It's dangerous to make measurements. And it's the main source of the system background. So we need to eliminate straight line, especially for some weaker straight lines can make a big interference, and we also can reduce the dynamic range. And next is the integration time and sampling speed. So strong single node and short pulse, we need to focus the shortest integration time. For like iron luminescences. And also we have the weaker single node. Weaker single node is we need the longest integration time. Take SLR camera for examples. If you want to measure the voltage, it's needed to use the fastest shuttle speed. However, if you want to take a picture of the star, you want the longest integration time. And next is the sampling speed. What's the sampling speed? Sampling speed is the how many frames of reprint spectrums can be acquired per second. Especially we can say some spectrometers have over 1,000 frames per second. So finally is the stability. When mention about stability, we also always mention about temperature stability. So every change 10 degrees of the temperatures, we can see how much intensity, how much percentage of intensity change. And we also ask how many wavelengths shift in nanometers. And we have a long time stabilities. All these factors affect, all these 8 factors can affect the spectrometer's performances. However, there are also some integrated algorithms, and so on. We cannot introduce all here. So next lecture in detailed introductions of the wavelength range. Firstly, we have to refer to the wavelength range formula. We use the start wavelengths to divide to the end wavelengths. So when the optical path topological is fixed, so wavelength is mainly decided by the grating lines. So the more the grating lines, the narrow the wavelength ranges. And when the grating lines are fixed, wavelength ranges can be adjusted by adjusting the grating bias angles so that we can move the whole wavelengths on the left and move it on the right. But the total wavelength range is fixed, just can move left and move right. Take examples. We can use when we change different grating lines. So we have an experience formulas. We have an experience formula. It may not be 100% accurate, but it's very useful. L is the grating lines, and R is the wavelength ranges. So if we have ATP 2000 MP, wavelength range is covered from 300 to 1000 nanometers. So the wavelength range is about 700 nanometers. If we use the grating lines of 500 nanometers, so the question is, if we change grating to 1200 nanometers, what's the wavelength range? So we can use the 500 multiply 700 and divide 1200. So it's less than 300. So wavelengths, if you use the more grating lines, and wavelengths will be shorter. Next, we are going to introduce the 3 definitions of resolution. We have to confess that most customers have messed these 3 types of definitions up. So some suppliers might use the pixel resolution as the optical resolution, and they use the wavelength resolution as the optical resolution. Even worse, so if the customer cannot familiar with these 3 types of definitions, he could take a risk of being treated by the supplier's resolution value. Here, so we emphasize the 3 types of definitions to you. Firstly is the optical resolution. Optical resolution is the used most by the because it used to indicate the light spreading capacities. This is the denote the you can see this is the peak height. It's the peak height. We use the half height, and the maximum, and this yellow one is the FWHM to indicate the optical resolution. Optical resolution. This is the real optical resolution. Some customers may use the half height like this. Half height and half wise. So pay attention to half this one. Although it's shorter, so resolution is better, but it's not real. It's not real optical resolution. Customer should pay special attention. So we need to list the full maximum height to FWH.M, full width and half maximum to indicate the optical resolution. And second one is the pixel resolution. Pixel resolution is a virtual notion of resolution. It depends on the dictator's pixel. So the more the pixel numbers, the resolution is better. So in OptoSky, we have if we want to improve the resolution performances, we can use the end you can use the end divide to the start and divide to the pixel. So resolution, the more the pixel, the resolution value is smaller. Smaller resolution value, the better the resolution. So if we have a one spectrometer range from again 300 to 1000 nanometers, the dictator pixel is 2048 pixels. So the pixel resolution is only 0.34. This is the pixels. This is the pixel, and this is the pixel. It's here, and this is the pixel. So the distances of the pixel. This is the pixel resolution, but this is the optical resolution. Obviously, optical resolution is bigger than pixel resolution. And the third one is the wavelength resolution. Wavelength resolution can respond the wavelength center of the gravity change. It mainly applies to wavelengths measured of the laser wavelengths. It can use algorithm to calculate the spectrum center of the gravity. We use algorithm to calculate, but the wavelength resolution is far smaller than optical resolution. We have a optical resolution. This picture is 2.8 nanometer, and pixel resolution is 0.57, but wavelength resolution is only 0.05 nanometer. So according to our experience, wavelength resolution is only about 1/10th pixel resolution. So wavelength resolution is a value is smaller than pixel resolution and smaller than optical resolution. So this resolution can be 0.05 and 0.35 and 1.3 nanometers. So that's why we have to emphasize the resolution. So if you use the wavelength resolution to replace the optical resolution, so you can imagine what kind of spectrometer's performances will be. And also this picture is the optosky's wavelength optical resolution. The highest optical resolution, we use this here. Half wise HM. We can have a 0.367. This is the very super good resolution in the industry, and our use the FWHM. So if some suppliers use half wise and half maximums to name half wise and half maximum, this one to say that you have to able to tell it is an error and it's wrong. So pay attention to FWHM, full wise and half maximum. So we have introduced we are going to introduce what are main factors affect resolution. We have introduced the resolution. There are three types of definition, and resolution is very important. So how can we improve our resolution? Firstly, we can select a better optical platform. M-shaped CT optical paths have a better resolution. So we can use the M-shaped, we can improve the resolution. Cross CT have a higher sensitivity. So improve, we can use M-shape. And we can have a more dictator pixel. And we mentioned before, the more the pixels, the higher the resolution. If we use the 4096 pixel dictator, the resolution will be better. So because it's the pixel resolution will be better. And also we have slitwise. So we say that the narrower the slitwise, the better the resolution. So we can narrow the slitwise to improve the resolution. That's why it's a grating line. If we use the more grating lines, the resolution will be better. So all these four factors can can be selected to improve the resolution. And this is Optosky's high resolution model, like ATP 3040. It has a 4096 pixels, and it also uses the CT cross, and this is one also very super high resolution because it uses the M-shaped optical path, and it also have a 4096 pixels. So after introducing the resolution, and we have to mention dynamic range and signal to noise ratio, because many people mix these two parameters. Customer may say that signal to noise ratio equals the maximum peak height. The maximum peak height is 1 in 918 nanometers. To divide to maybe we have this noise readout. To divide the noise RMS. Actually, this is not the signal to noise ratio. It's the dynamic range. It's a wrong formula. But why the customer use it frequently? Still use it because it can reflect a partial performances of a spectrometer. Firstly, it's very easy to measure. It's only need to acquire a spectrum. So it's measure a time, and you can obtain this value. And secondly, it fully complies with the human intuitive feeling, such as if the noise is big, so this value will be smaller, and if this is higher, and the value will be better. So it can fully comply with the human intuitive feeling, and these values also very useful for machine learning. So it can identify spectrum related to these parameters. So previously we introduced the long methods to calculate the signal to noise ratio. But so what's the correct methods to test the signal to noise ratio, especially in quantitative analysis? Firstly, it's needed to perform continuous acquisition. We say continuous state over 100 times acquisition. Firstly, we get a sample, and secondly, we set the test condition, and we make over 100 times of continuous acquisition. Then we can have this. We can fetch this peak, and we can light it in a line. 100 light it in a line. And secondly, we use fetch the maximum peak and light it in sequences by the time. So we can have it, and then we can obtain the average values, and we have the average value to divide to the time. So we can know the signal to noise ratio. is is this is the correct method. So it's very, we mentioned before that the dictator is very important. So we have to introduce some core dictator technologies. From this picture, all this is the dictator. By looking at the outlook, we know this is the first stage core dictator, and this is two layers. Is the two-stage cooler, and this has three layers. So we have the three-stage cooler dictator. And what's the principles of the dictator? Principal dictator actually is just like this P and not, like this P and not. Suppose if the light shoot on to get through here, we can have this. This is the have a cooling, get a cooling result, and we can transfer this heat to here. So here is a heating port. So it can transfer the heat to this, to ventilation. Suppose if we can reverse the electric current from this side. So we can have this is the heating, and this side we can make it the cooling. So it can just transfer from here to here. And also this one is the high-end dictator because it uses the metal platform. And this is because this is the have a it cannot generate so much heat, so we don't need to use metal. We can use the CMOS. Is this we can have use the plastic housings. In order to let you know more about the core dictator's benefits, we can introduce you. So what can core dictator bring us? Firstly, you can see from this graph, is the different colors indicate a different cooling temperature. If in the shorter integration time, the cooling temperatures has little differences. However, with the gradually rising integration time, the darker efficiencies is different. So the quart, if quart minus 20, the dark current is also very low. However, in room temperature, it's such high. Dark current is such high. So it has such a big differences of dark current. We turn to the left graph. We can see the dark noise also can rise sharply with the temperature. So we can see if you are cooling minus 20, the noise is such low. And if you are rising up to this one, the noise is so big. So that's why the quart to minus 20 can have reduce the dark current and reduce the noise. And Optosky ATP 6500 can cool down to 15 degrees, and cooling temperatures can to 1.3 hours. And for ATP 5020, we can cool down to minus 5, and it can cooling time up to 10 minutes. And we need to take more examples of Optosky ATP 6500 dictator. We can see that when cooling down to the 100 milliseconds, The dark current is only 80 counts, but the noise is only 7, is very low. However, if we integration time increase to 10 seconds, the dark current increase to the 245, and the noise is 10, also very low. And if we increase the integration time to 60 seconds an hour, dark current only just have 1100, and the noise is just 30. So you can see why ATP 6500 is costs so expensive, because the performance is very good. It's very easy to run the spectrometer over an hours, and the dark current and noise is fairly good. So after introducing a dictator, we have to make a comparisons of the reliabilities. This is the optosky's spectrometer's design. We have separated the optical rooms and with the PCB board room. So within the middle, there's a metal platform. All optical components are fixed on the high stabilized metal platform. Just stabilizing the metal platform, this one. This one, metal platform. And this way can prevent volatile matters heated from electrical paths from polluting optical performances. We can see that the expansion and contraction ratios metal platform is only 18. However, our competitors usually fasten the optical path directly on the PCB board. You can see PCB board expansion and contraction ratio is 150-50. It's about 10 times higher than the metal platform. So we can see that the performances of the optosky spectrometers at least 10 times more reliable than the competitors. Although our competitors may use the cooled spectrometers to reduce these pollutions. However, cooled spectrometers have a larger size and big power consumption, as we mentioned before. And also, we have some reliability test figures. You can see that we have make the temperature stabilities. You can see our temperature stability to change rate, intensity change rate 0.37%. Is very good figures. And also we have a long time, 24 hours long time stability is only 0.14%. It's also very good. So all these data is good, can verify the optosky reliability. So we have introduced, next we have to move to the optosky modular spectrometers. This is the map for the UV visible and near infrared spectrometers. We have the ultra miniature ATP 1000 models. And it's just like Ocean Optics STS. And we have an ATP 1010. It is added the UV ranges, because STS also have no UV range. If you want a UV range and you want the compact size, you can choose this model. And also we have an ATP 1012. It's a xenon driver. built inside to drive the xenon. And also we have ATP 1200 is used the BTCCD. Performance is better. And we also have the most popular the ATP 2000 series. This series is the most high performances to price ratio. We have ATP 2000 P is just compete to the Ocean Optics 2000 plus, USB 2000 plus. And we have the ATP 2000 PD. The D is indicate built-in dark background shutters. Because when the customers to perform the measurements, sometimes they want to scan the dark background, but when the light source is on, it's not easy to do it. So we have this dark background shutters built inside to easily to scan the dark background. And also we have the ATP 2000H. This is frame rate can reach up to 4000 Hertz. And we have ATP 2002. This is a xenon driver built in model, usually for the water quality analysis and UV smoke analysis. And we also have the ATP 2100. It has the highest signal to noise ratio and compact size. And we have a higher resolutions, the ATP 3000 series. We have the ATP 3000, they use the cross CT, and we have the ATP 3040, use the 4098. And we used to compare this model with the Ocean Optic HR 4000. And we also have a M-shape cross CT. We have a ATP 3030. And because this is also the most ultra high resolution models. It has very high resolution and low straight line and looks just like this one. And we also have the ATP 5000 series. And we have an ATP 5020 PD. This one is compared to Ocean Optics Maya series, but performance is better than Maya because Maya is uncooled spectrometer, but ATP 5020 is the cooled spectrometer. And also we have the ATP 5030. It's usually M-shaped light path. The 5000 is longer because it's the cooled. And also we have the higher end scientific glasses. We use the FFT CCD cooled 6 series. 6 series we have ATP 6500. This one we compete with the Ocean Optic QE 654. And we also have ATP 6500 T3, means the 3-stage cooling temperature can cool lower than room temperatures, 55 degrees. And it's the 3-stage cooling. And we also have the ATP 6530. It uses the M shape and with the built-in D, means the built-in dark background scan shutters, and T-Sun and this. So Optosky have the most forward spectrometer series for the UV visible and NIR family. So whatever your application is, we can configure the best models for you. Let's move on to the infrared spectrometers. Firstly, we have the ultra mini ATP 8100. the performance is lower and the cost is lower, and we have a low cost uncooled NIR ATP 8600 series. And from this up, this is the cooled NIR, is a high performance ATP 8000, and it can peak to ocean optics NIR. And also we have a higher performances. We can cool to T3 stage. So from the ATP 8100, the lower performances, we move on to the higher performances. We have a 3-stage TEC. So you can also based on your budget and application to find the best models for your application. And besides, we are OptoSky also a few manufacturers can produce the MIR, mid-IR. We can cover it from 2.5 micrometer to 11 micrometer. It's uncooled para-electric. And this is our scientific class, modular spectrometers. We say that how to testify spectrometers manufacturer is good or not. You can see his high-end spectrometers. ATP 6500 is OptoSky high-end spectrometers. We have an M-shape optical path with a better resolution and a better straight line, ATP 6530. And we can have a 3-stage TEC to have a better resolution, better straight line, lower noise, and a lower dark current, and higher stability. And we have the ATP 6500 T3. It's a 3-stage TEC, cooling down 45 degrees lower than ambient temperature. And you have a lower noises, a lower dark current, and it's very stable. So, and now we already have the ATP 6500. So this year, in 2020, we will launch the ATP 6500 T3 in 2020. And maybe in before 2021, we will launch ATP T3. So you can looking forward to our new models coming. Finally, we would like to share some examples of applications with you. Actually, modular spectrometers can be used to many industries. We can have applied to environmental industry and in the industrial inspection, and used to the biomedical industry and scientific instrument. So for the environmental industries, we have the most common UV smoke analysis and water quality analysis. And not to mention industrial inspection, we can inspect the colors to sort out the colors. We can measure the transmittance, emissions, and laser wavelengths monitor. We can measure LED color. We can measure film thickness, and we can measure glass thick, and also process analysis technologies for our application. And also we have a biomedical industry. We have a ultra micro volume spectra photometers, and also fluorescence spectroscopy. And scientific instruments, we have fluorescence spectrometers, and we have chemical lighting and photoluminescence and LIBS and the liquid chromatogram. Surely the application cannot be limited in here. There are many more. But next, we are just sharing several instruments designed by the Optosky with you to see how these spectrometers are being applied. Firstly, is the UV smoke analyzer. The principle is very simple. You just use the light source like a deuterium or xenon pulse light source, and then this light source deuterium, although deuterium has a higher reliability, but it needs to replace the bulk every half years. So, but pulse xenons don't require to replace the bulk. It can use over 10 years. So more and more people use pulse xenon for the light source. So the light source goes through the fiber to access to the spectrometers to make a measurement, and the smoke can shoot on from this port to here to make an analysis, and exhaust take the gas from this side so the spectrometers can make an analysis in here and export a spectrum. And the spectrum readout is this one, just like this one. And this is the we can by calculating the alpalitide, we can know the concentration of the this part. So for the smoke, we have oxygen nitrogens, mainly for the 220 to 245 nanometers, and we have sulfide oxygens covers from 200 to 220 nanometers, or 260 to 280 nanometers, and we also have oxygen nitrogens cover from 420 to 440. Besides this, Optosky provides exclusive wave shaping technology. You can see this is the original spectrum. We can see in UV range, the intensity is very low. After reshaping this, we can have a higher intensity, just like this one. So the wave shaping intensity can make the shape looks more elegant. Next, let's move to Optosky's multi-parameters water quality analyzer. This ATE 2000 is Optosky self-developed reagent-free multi-parameters water quality analyzer. It can use to detect COD, BOD, and also nitrate, nitrogen, ammonia nitrogen. And also we have a metal. We have a metals detect. And the principle is also very easy. You just use a light source. You can use the pulse xenon or deuterium, and goes from the fiber to this is the liquid. This is the liquid samples. When we immerse this instrument to the river, it will expose this to the water. So we can measure these liquid samples by the spectrometer to read out the spectrum. And later, Optosky has the actual microvolume spectral photometers, nanobio 200. This is the biggest spring. Its actual volume it just needs 0.5 to 2 micro liquid, and its dictate speed is very fast, just 3 seconds. And also it's usually a larger screen. And battery can last 10 years. And we welcome the OEM production, and it's 5. So in order to show you principle on nanobios 200, we make a flash. Okay, this flash cannot work. So let's change. Let's see if it works. Okay, no, sorry about that, but that's fine. We can move on. Okay, 死机了。Okay, fine. Sorry about that. And we move to laser wavelength analyzer. We have mentioned this before. It's a very easy ATM 3000 wavelength laser, so we don't introduce here. And we also have a micro area fluorescence spectrometer, and in this ATF 8100 autofocus and scan, we have the actual large view FOV view of viewers, and we can see this is the platform inside. This is the platform, and this is the sample cell. Tissue cells, and if we have a laser LED shoot on the tissue cell, it will generate the fluorescence, and fluorescence can be shoot up to this here, and we can use the spectrometer to make analysis, and use this camera to have vivid pictures. And you can see this anion epidemics pictures, and this is the spectrum. So this is our micro areas fluorescence spectrometers. And also people use spectrometer to measure the glass thick. And firstly, we have the broadband source to coming down to this way, and different wavelengths will shot on this point, and we put on the glass here, and the upper surface and the lower surface will have generated the strong reflectance, so it will have a sharp peak. We can deduct this peak, show the distances we can obtain the glass thick. It's a non-contact, so many customers use this method to measure glass thick, and not to mention thick filmed measurements meter. And we also use this principle is we can use the thin film refracting. We can generate the reflectance to measure the thin film to make a measurement. This is our software, and this is our model numbers. Finally is the reflectance and transmittance and absorbance analyzer. We have the ATP 7100. It can realize online, in-still, and flow monitoring. And this is the principles. We have this is dictator zone. Just have a measure optical path to have a measurement probe. This is the probe to put down here, and light source to go in here, and the spectrometer can make analysis of this spectrum. And also we can change change the change the this one, and also change this one to realize the online measurement. So that's it. Thank you. Next, we are going to pass my microphone to my colleague, and we are going to show you, present you how to obfuscate modular spectrometers will work. So for the YouTube customers, we are going to start here because I cannot transfer the lecture to blind, but we will upload this video later on YouTube to you. So, bye-bye.